For as long as I've been following electric vehicles, there's been this one running joke in the industry.
Oh, the famous 5-year rule.
Exactly. It goes exactly like this.
Hmm.
The ultimate, perfect, revolutionary solid-state battery is always, without fail, exactly 5 years away.
Right. Yeah, it just keeps getting pushed back.
It's an automotive mirage that just keeps receding.
Mm-hmm.
But, thanks to an absolutely brilliant stack of research provided by you, our listener,
Who we like to call the learner, right?
the learner, yes.
Yeah.
Today's deep dive proves the mirage is finally real.
It really is. It's happening now.
Yeah, we are looking at a genuinely clever mix of sources today. We've got international press releases, hard market data out of China, some incredibly detailed Italian spec sheets, and like a few heavy-hitting deep tech articles.
It's a great stack. Really comprehensive.
It is. Collectively, these documents map out what is undeniably the biggest automotive shift of the decade.
Without a doubt.
So, our mission today is to decode exactly why 2026 is the year that this eternal 5 years away promise has actually become a reality. You can go out and park in your driveway.
Finally.
Okay, let's unpack this because before we talk about the actual cars hitting the dealerships, we need to establish exactly what is changing.
Right, the chemistry itself.
Yeah. To appreciate the scale of this, what's actually physically changing inside the battery?
Well, the lithium-ion batteries that have powered everything, from your laptop to almost every EV on the road before this year, they rely on a liquid electrolyte.
Right.
And that liquid serves a crucial function, obviously, but it brings severe physical limitations.
Yeah, I always picture the traditional liquid electrolyte as kind of like a leaky water balloon.
A leaky water balloon, yeah, that's a good way to put it.
Right. Like you have this liquid that shuttles the ions back and forth, but it's inherently volatile. It's fundamentally a fire risk.
Exactly. And a solid-state battery, by contrast, takes that chaotic fluid highway and replaces it with a highly structured, rigid material, like a ceramic or a polymer.
Right. A ceramic solid polymer or a sulfide. And what's fascinating here is the sheer cascade of downstream consequences that stem from that one seemingly minor material change.
Because it's not just a small tweak, right? It changes the whole game.
It changes the entire physical profile. Because you engineer out the fundamental fire risk at the chemical level, the safety constraints holding back performance are just, well, they're instantly lifted.
Wow.
Yeah, so we are suddenly looking at a 30 to 50% jump in energy density.
30 to 50%, that's insane.
It is. And the charging speeds roughly double.
Because you aren't worried about the liquid boiling or, vaporizing under high current.
Exactly. The solid matrix tolerates incredibly high current densities. Plus, the cycle life stretches out to 2,000 or even 3,000 full cycles.
Wait, really? 3,000 cycles?
Yeah, in certain conditions.
Yeah.
Because you remove the secondary chemical reactions that break down the liquid over time. Okay, that structural shift makes total sense. But I do need to clarify something, because looking through the sources, specifically the SAIC and MG data regarding their SolidCore tech.
Ah, right, the manufacturing stepping stone.
Yeah. The cars rolling off the production lines today, they aren't actually 100% solid, are they?
No, they're not. The immediate reality we're seeing in 2026 is actually semi-solid.
Okay, semi-solid. What does that actually mean in practice?
Specifically, it's a polymer inorganic composite electrolyte. It's basically 95% solid and about 5% liquid.
Okay, so 5% liquid, that feels like a very deliberate choice.
Very deliberate, yeah.
Because building a completely solid ceramic battery at scale millions of units must run into contact issues, right?
Exactly. Achieving microscopic perfect contact across millions of square meters of rigid battery layers is a manufacturing nightmare.
Right. If there's even a tiny gap, the ions just can't jump across.
Exactly. So that 5% liquid acts as a wetting agent. It fills in the microscopic gaps and drastically reduces the interfacial resistance.
Ah, okay. So it's the perfect mass-producible bridge.
Exactly. It leverages existing gigafactory capital. You don't have to rip out billions of dollars of equipment. You just tweak the existing lines, but still deliver next-generation performance.
Which naturally leads to asking, who is actually managing to put this science experiment onto the road today?
Well, the Chinese automakers really aggressively funded this transition.
Yeah, let's look at the SAI MG4X from the sources. Because this B-segment SUV hit Chinese dealers in May of 2026.
It did.
Yeah, and it has a 54 to 64.2 kilowatt-hour semi-solid pack. The starting price for this thing is the equivalent of 14,700 US dollars.
Which is just, I mean, it completely upends the traditional cost curve.
14 grand for next-gen battery tech. That's mind-boggling.
It is, and it's not just staying in China. The Italian spec sheets in our stack show this exact same tech hitting Europe by late 2026.
Oh, as the MG4 EV Urban.
Yes, delivering around 400 kilometers of WLTP range and backed by a 7-year guarantee.
Okay, here's where it gets really interesting for me. Yeah. I'm looking at the safety data for that European rollout, and I've got to push back a little here.
Okay, what stands out?
The needle penetration test. Wait, so you can literally stab this battery with a steel needle for 2 hours and nothing happens?
I know it sounds like PR spin, but yes.
Because with a standard liquid lithium-ion cell, if you drive a nail through it, it short circuits, the liquid vaporizes, and it violently erupts into flames.
Right, thermal runaway. But the absence of a volatile solvent fundamentally alters that physics.
So what actually happens when you puncture this semi-solid matrix?
A short circuit does occur, and you get localized heat. But that 95% inorganic composite doesn't vaporize into a flammable gas.
It just absorbs the heat.
Exactly. It dissipates the heat without triggering a cascading fire. They monitored these cells for 2 full hours post-puncture. The result was literally 0 smoke, 0 fire, and 0 explosion.
Wow. That completely eliminates the thermal runaway fire risk. That changes everything about how we design cars.
Absolutely. But the safety from heat isn't the only extreme we're seeing. Dongfeng Motor is pushing the cold weather extremes.
Right, the Mohei testing.
Yeah, Dongfeng has a rival 350 watt-hour per kilogram battery. They're targeting mass production for September 2026.
And to prove it works, they took it to Mohei, China, which is brutally cold.
Subarctic. They were running calibration tests at minus 40 degrees Celsius.
Minus 40. See, in a traditional liquid cell, the electrolyte basically turns to syrup at those temps.
Exactly. Which is why EVs historically lose 30 to 40% of their range in freezing weather.
Right. But the data point that absolutely floored me in the sources, at minus 30 degrees Celsius, the Dongfeng battery maintains a 72% energy retention rate.
It's incredible. The solid polymer matrix doesn't freeze or get viscous like a liquid.
So the ions just keep shuttling back and forth.
Yeah, with remarkably high efficiency. This fundamentally changes EV viability for drivers in Canada, Scandinavia, or, the northern U.S.
The historic winter range penalty is just gone.
Effectively neutralized.
Okay, exceptional safety and surviving the Arctic tundra. Those are huge technical wins.
Yeah.
But how does this fundamentally alter the day-to-day lifestyle for you, the driver?
Well, the biggest lifestyle shift is that range anxiety is effectively dead.
Real. Dead completely. I mean, look at the IML6 Max from the sources. It's already delivering 1,000 kilometers of range on a single charge.
1,000 kilometers?
Yeah. But honestly, the raw range number isn't even the most important part. It's the charge time.
Right. The speed at which you can put that power back in.
Exactly. Because this battery can accept ultra-high current without melting, we are looking at 10 to 12-minute charge times.
10 to 12 minutes.
Yeah, to go from 10 to 80%.
Which makes an EV charging stop functionally indistinguishable from a petrol stop. Exactly. You plug in, go to the restroom, grab a coffee, and you're ready for another 500 kilometers of highway driving.
I have to point out a detail here for the car lovers, too.
Oh, the weight reduction.
Yes. For years, performance EVs have been held back by their own mass. But because of that 30 to 50% jump in energy density, you can drop 200 to 300 kilograms of battery weight.
Which changes everything about the physics of the car.
Right. The suspension works better, braking distances drop, and a performance EV can finally handle like a true sports car again.
Yeah, instead of a heavy sedan trying to hide its weight with software.
Exactly. Okay, I need to pause our celebration of the engineering here.
Uh-oh, here it comes.
Yeah. So what does this all mean? Is there a catch? Because the industry isn't a utopia?
No, it's not. And if we connect this to the bigger picture, the sources outline some pretty harsh realities for early adopters.
I figured. What's the biggest hurdle?
Manufacturing scale is incredibly difficult. It's one thing to make a few thousand perfect cells for test cars. It's another to reliably pump out 200,000 packs a year.
Which means early buyers are going to face massive supply constraints.
Exactly.
So even if the starting price in China is 14.7, when these hit global markets in limited numbers, dealer markups are going to be absolutely brutal.
Astronomical. And compounding that is a looming marketing issue.
The semi-solid label.
Right. The semi-solid label is going to be heavily abused. because there's no strict regulatory definition right now.
So legacy automakers could just squirt a tiny bit of polymer gel into an old liquid battery and call it next gen.
That is exactly what will happen. Slap a semi-solid badge on the back and charge a premium.
That is so frustrating. Consumers are going to have to really read the fine print.
They will. But the most terrifying catch highlighted in the deep tech sources is the cost of out-of-warranty failure.
I was afraid of this.
Yeah, these are monolithic structural components now. If a cell fails out of warranty, you can't just swap a small module.
Right, because it's baked right into the chassis of the car.
Exactly. The current estimated replacement cost for these Vanguard semi-solid packs is between 40,000 and 60,000 pounds.
Wait, 40 to 60,000 pounds.
Yes.
That effectively totals the car. If you get a bad cell in year 8, the repair costs more than a brand new vehicle.
Which is why that 7-year guarantee we mentioned earlier isn't just a marketing perk.
No, it's an absolute financial necessity.
Exactly. You carry a massive financial risk if you're an early adopter, and the future physically breaks.
Man, okay. Even with those massive hurdles, though, the supply issues, the markups, the deceptive marketing, the scary replacement costs, we really have to recognize the scale of this pivot.
Oh, absolutely.
2026 is undeniably the tipping point. We've gone from the lab to real-world needle penetration tests to surviving minus 40 degrees in Mohe.
And all the way to $14,000 semi-solid SUVs actually sitting in showrooms today?
It's incredible. And fulfilling our specific mission for today's deep dive, I explicitly want to thank you, the learner, for providing such a clever and engaging stack of articles to explore.
Yes, thank you. The research was fantastic.
It really was. It let us learn something entirely new about a massive shift in the industry. Thank you for your time and for listening to our deep dive.
Before we sign off, though, I do want to leave the learner with one final unmentioned concept from the sources to mull over.
Oh, lay it on us.
The sources mention that Toyota is targeting a 2027 launch for their 100% solid-state packs.
Okay, next year.
Yeah, but their engineering target for those packs is a 30-year functional cycle life.
Wait, 30 years?
30 years!
A normal car chassis is completely worn out after 15 years.
Exactly.
Yeah.
So if a car battery can soon outlast the chassis it's built into by decades, will we soon see a future where you buy the battery for life and simply swap the car shell around it every 10 years?
Wow. That changes absolutely everything.